Welcome to the overview video and introduction to the course Special Relativity and Electromagnetism. My name's Dr. Paul P. Cook and I'm going to be your lecturer through the medium of video for this course. Now this is a course with two titles, Special Relativity and Electromagnetism, so two topics in the title, and it's going to be 80% electromagnetism and perhaps about 20% special relativity. The two subjects are intermingled. In fact, all of the possible transformations of special relativity are arguably already apparent within electromagnetism. And the mathematics of electromagnetism is beautiful in and of itself. It is the mathematics of vector calculus, really put into practice in an advanced setting. I'm not going to talk too much to you about the history of the subject in this course because it's vast. And there's also a lot of material to talk about in the course. But let me give you a short overview now. Let me begin by reading you a quote from a very famous physicist called Richard Feynman. He says at the end of his first lecture on electromagnetism, he says, "From a long view of the history of mankind, seen from say 10,000 years away from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison with this important scientific event of the same decade." So part of this course will be to try to convince you of the importance of this subject. Okay. But it won't be the foremost aspect of the course. This is a course in mathematics, and we will use mathematics in various settings in order to solve problems relevant to electromagnetism. Let me tell you a little bit about the history, though, now. So here you see James Clerk Maxwell, after whom Maxwell's equations are named. So he lived from 1831 to 1879, and he was at King's College London when he did his most famous work from 1861 to 1865. You may have seen the plaque in the Strand building commemorating his work. You might have seen the equations on the walls of the canteen. So the theory of electromagnetism was discovered by James Clerk Maxwell while he was at King's College London, and Maxwell's equations themselves were published in the current form we understand them in 1865. Prior to Maxwell's work, the electric force, the magnetic force, and all kinds of electromagnetic radiation, so light and radio waves, for example, were understood to be distinct aspects of the natural world. What Maxwell did was to unify electrostatics, the forces due to static arrays of electric charges, and magnetostatics, the forces due to a static magnetic field. His unification was brilliant, and he did it by understanding that the motion of electric charges interacted with magnetic fields. By introducing dynamics and relative motion into the study of electrostatics and magnetostatics, Maxwell could show that electricity and magnetism are in fact two faces of a single underlying idea called electromagnetism. As a result of his unification, Maxwell discovered that light and radio waves are forms of electromagnetic radiation as well. Much of the modern world, therefore, is underpinned by the revolution in thought and engineering that Maxwell's electromagnetism brought about. Let's have a little look at the equations. So here we see Maxwell's four equations. Now, parts of these equations were known before. I'm going to use this list of equations to give you a brief overview of the path we'll take in studying electromagnetism. So we can see here the first law is written in terms of the divergence of E, a vector field, okay, gives us rho over epsilon 0. So much of this here is going to be obscure to you right now, but I want you to notice E, which stands for the electric field, and B, which stands for the magnetic field. And you see these are equations that are relating the two different types of fields. Notice also at this stage there are terms which involve time and change. So see the two terms in red, the dB by dt and the dE by dt term? Well, Before Maxwell, these weren't properly understood. The dB by dt term was understood by Faraday. But if you just bear with me for a moment, imagine that we set the two terms in red to 0. Now if we did that, we'd have the curl of E is 0, and we'd have the curl of B is mu0 times J, and nothing else. Okay? The equations which are relating B and E would decouple, because it's only when there's a d by dt that we see B related to E, or vice versa. So there's a setting called electrostatics in which the electric field E doesn't change. There's similarly another setting, the magnetostatics, where the magnetic field doesn't change, where we can set those two terms to 0 and study magnetism and electrostatics separately. And that's what we're going to do. Now you do not need, before we begin this course, to understand anything about the physics of the setting. Here are the equations for electrostatics and magnetostatics separately. What we'll do is we will begin with some equations which are known empirically, not many, probably just two. One that tells us how to work out the force for a static array of electric charges, known as Coulomb's law, and another one which does something similar for static magnetic fields, known as the Lorentz force law. And our aim will be to pursue ideas and logic and perhaps a little bit of what's known from experiment to modify the equations exactly as Maxwell did. Okay. So here is Coulomb's law writ large. So Coulomb's law was known empirically, and it relates an electric field, which is a series of, let me focus on the electric field down here. Here is the electric field E. Now what it involves is S is a vector, S hat stands for the unit version of S. Now we have several of them labelled by I. Now S stands for the separation between little q1 and big Q. That gives us S1. Little q2 and big Q, the separation vector, going from little q2 to big Q is S2, and similarly for S3, but for a third charge Q3. What Coulomb's law tells us is when there's a set of source charges, little q1, little q2, little q3, for example here, and then we put a test charge, big Q, in the middle of them, what force does that test charge feel? So far, so very physical. But in writing down what the force is, we're working with vectors. And indeed, to try and compute for more complicated arrays than this, the field, the vector field needed to give us the force, we will have to resort to more and more ingenious ideas. So we'll perhaps be motivated by the physics to say, let's try and work out what the forces are on this system, in which case, if we know the forces, we can solve the dynamics, thanks to Newton's equations. But we will find more and more frequently that we will come up with examples where it's better for us to work with the electric field rather than the force directly, and then after that, the potential, the electric potential. Now all these things and our ways of thinking about these ideas, despite them being in the setting of the physical universe and us talking about physical things like charge and charges, actually will all be written down and thought about in the language of vector calculus. So this course, despite its connections with physics, will involve you mastering your knowledge of vector calculus. This is why the course will begin with 1 to 2 weeks of essential revision of material that you've studied before about gradient, divergence and curl, but refamiliarizing you with the subject. And we'll also do examples which bring us ahead in our thinking that will help us for thinking about electrostatics. So this will be roughly our idea, and this is how we'll approach the subject as mathematicians. We'll take some equations that are empirically known, Coulomb's law, and here below I'm drawing out the Lorentz force law for you, which relates magnetic fields and the motion of charges, and explains why two wires with currents passing through them will either draw each other together or repel, depending upon whether the currents are parallel or anti-parallel. So we'll begin with these two vector equations. Those will be our axioms and our input. And then on top of that, we will add our knowledge of vector calculus in order to develop more and more intricate ways of trying to find the electric field. Okay, so in our review we will immediately cover Green's theorem and Stokes' theorem again, and then we will use them again and again throughout the course. Another consequence of Maxwell's work, though, was the discovery that the speed of light is a constant. Now, this idea had to wait about half a century before this man, Albert Einstein, could, there we go, there's Albert Einstein, before Einstein could outline all the consequences that it entailed. So in 1905, Albert Einstein published, well, he published many papers in this amazing year that were phenomenally influential. But in particular for us, he published a paper outlining his theory of special relativity. And he had two postulates in the theory of relativity: that the laws of physics apply in all inertial reference frames in the same way, i.e. it doesn't matter if I'm moving with relative speed to you, we can still talk about the laws of nature and apply them similarly and take account of that. Our relative motion can be taken account of. And then his second postulate was that the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the source. Now this second thought is slightly bizarre. At least it's bizarre until you've understood its necessity. I mean, it's telling you that suppose you're driving a car at near the speed of light. Okay, I know that's not possible, but suppose you're driving a car at nearly the speed of light and you turn the headlights on, then the speed of light emitting from the headlights doesn't add in the normal way, because you can't add c, the speed of light, to something near c and get anything above c. It has to always be below. So weird things will happen necessarily because of the constancy of the speed of light. And some of those weird things are that time will be dilated, so time will slow down in frames which are moving with respect to each other. Lengths will contract and shorten. We'll also come to accept that the natural setting for all of these thoughts is four-dimensional space-time. Space and time get joined together. And the equation, the most famous perhaps equation in theoretical physics, E equals mc squared, will emerge naturally from a consideration of the length of certain vectors. So these are huge changes in perspective. These spectacular predictions will not only lead to changes in the experimental world, but also changes in the mathematical world. In particular, because it is useful to physicists, four-dimensional geometry historically gets studied much more deeply by mathematicians. So, to try and make a connection with mathematics from what seems like a very physical course, we are going to be studying these two subjects, electromagnetism and special relativity, in the maths department. And even though it sounds much more like a degree in physics, if you think a little bit about the history above that I've talked about, you will hear so many things related to the physical world and experiment that it might seem a little bit off-putting. But I promise you, all our work, most of our work, will just take the physical equations as axioms, and we will build upon that with mathematical thought and reasoning. This idea of having thought experiments to develop thinking was immortalized by Albert Einstein. He made a number of major developments by thinking about Gedanken, or little thought experiments. What would happen if? He didn't perhaps think about the car driving near the speed of light, but he thought about all sorts of very creative ideas that led to deep, deep ideas. That's almost the path we will take. We will not resort to experimental apparatus, nor to looking up tables of results. We will just develop ideas by thought alone and by mathematics. Okay. So, what is there to appeal to you in this course as a pure mathematician? Well, the most natural result for a mathematician studying these ideas will first perhaps be it's a laboratory for mastering vector calculus. Stokes' theorem will be used again and again in more and more creative ways. And it's also a setting in which your thoughts will naturally turn to thinking about geometries which are different from Euclidean three-dimensional geometry. Now, it's a little bit hard to understate how pivotal that idea has been in your maths education to date, most likely. When we talk about geometry, we think immediately of things which are preserved by groups of transformations in Euclidean space. As soon as we start thinking about four-dimensional geometry, some of the most fundamental ideas change, and as soon as we add curvature into that setting, it gets even more involved. This leads you most naturally to an interest in differential geometry, a subject which you can study later on in your degree. So, if you like, these first thoughts about work in a four-dimensional space-time will be a precursor, a sort of a small taster of what the beginning of studying differential geometry may be like. It should certainly raise in your mind questions that will need differential geometry for you to answer correctly. Okay, so these are the major appeals if you're approaching this as a mathematician. Okay, and I think the appeals if you're approaching this as a theoretical physicist or applied mathematician are evident. Okay, all of the maths that we will do will be done in a setting which could be applied and can be thought about in an applied setting. So let me now talk you through a very rough overview of the course. So you'll see before you a list of topics, and let me look at the broad topics first on the left-hand side. So you can see there's 6 large topics. Vector calculus, which will be a revision, which we'll study in the first week and maybe a little bit into the second week. Then we'll meet electrostatics, which will be our setting for playing with our knowledge of vector calculus. It will quickly become apparent to us, because of vector calculus, that it will be simpler sometimes to work with potentials, and then we'll have questions which arise immediately. How do we compute the potentials in certain situations? After that, we'll start looking at the other part of electromagnetism, the magnetisms part, and we'll look also at magnetostatics. We'll do something similar. And then finally, we'll join things together, and we'll have electrodynamics in the last part of the course and special relativity together. Okay. Let me give you a more detailed discussion of some of these points that we'll look at. So in vector calculus, we will just immediately, to refresh our memory and to also make sure our notations are the same, look at the gradient, the divergence, and the curl. One thing that's new that we will do is look at component notation. And we will give special conventions for doing that. And we will start using something called the Einstein summation convention, which will make our equations look a lot simpler. We will review line, surface, and volume integrals, and the fundamental theorems of calculus related to the divergence and the curl and the gradient equations, which give us Green's theorem and Stokes' theorem. We'll also meet something else which might be new, the Dirac delta function, and we'll see that we really need this object, as unusual as it will be, in order to think about some of the most fundamental fields in electromagnetism. When we start looking at electrostatics, our path will be like this. We'll take Coulomb's law as given, and then we'll try and use it. We'll try and work out some electric fields for some given examples. And our knowledge of vector calculus will lead us to Gauss's law, which will give us a great simplification for things we can think about. We'll then meet the electric potential, and we'll think a bit about the question of whether an electric field is something which is real. Now, although we're doing a maths course, this question is just naturally interesting, I think, because it's something that will be computationally useful for us to use, but it will be fascinating to try and argue the case that it is or isn't real. Okay, in the sense of, is it a physical thing in its own right with its own qualities? And one of the arguments in favour will be to talk about work done by the electric field, or the energy of the electric field, and so on. So we'll think a little bit about these things, and we'll make some comments on conductors. We will not do an awful lot of work on the electric field in solids in this course. Quickly, we will turn to thinking about potentials as ways to work out the electric field. We'll meet Poisson's and Laplace's equation, and then, under certain boundary conditions, we will try and solve those equations. And we'll meet in particular the method of images, which is a clever method for helping us solve more convoluted examples. And we'll apply the separation of variables to Poisson's equation and the multipole expansion, see what we can learn. Then we'll turn to magnetostatics, and we'll begin in the same way. We'll start with an empirically given force law called the Lorentz force law. We'll then think about the magnetic field, we'll think about its effect on currents, and we'll meet other famous physical laws that will all feed into Maxwell's equations. We'll do the same kind of analysis. We'll look at the magnetic vector field, and again, we'll look at equations and how to solve them under certain boundary conditions. Finally, we'll start allowing things to move again. Now, if you remember at the beginning of the video, there were these two terms with d by dt in them that I said we would study for a while by treating them as zero, so static fields. Now you can see this is an interesting setting. It seems completely artificial if Maxwell's equations are the real ones. I.e., what am I saying? Imagine we have an array of static charges. Well, already that's a hard problem, because don't like charges repel and dissimilar charges attract? Yes, so how can they be static? They're going to have forces acting on them. Okay, well, we'll imagine there's a setting that we can use to maybe hold the charges still while we're going about setting this stuff up. Okay, so there's an array of charges somehow held still for a moment before we're going to use the Coulomb law. The Coulomb law tells us the force on a test charge that we will bring in, our own big Q, and we'll put inside that electric field, and we'll try and work out the force immediately on it. So we'll be able to work out the dynamics immediately of our test charge. But clearly, and as we've alluded to, the signals that transmit the force travel at a finite speed, the speed of light. So when we're saying we can work out the instantaneous force on a charge Q, okay, due to an electric field, then what we're actually saying is something really, really contrived. We're saying, well, if we could just so arrange it so that we could just immediately work out the electric field, then fine, we can do it. But clearly, in reality, signals will take some time to go from the test charges, the source charges, to our test charge Q. So what will matter to the test charge is the array of charges in the past. Okay. And what we'll have learned from magnetostatics is also that whether those charges have some velocity will matter as well. So here's the really odd setting we'll have been working in all this time. We'll be saying to ourselves, to have worked out how Coulomb's law is applied, we think about the situation in the past and also how things were moving in the past in order to come up with an instantaneous static situation that could be applicable. Okay, so it's very contrived, and we will have by this point in the course spent a long time working on it. We do it because all the ideas that come out are very informative to us and will inform how to go about correcting things when it comes to wanting to have dynamical systems. This is what electrodynamics does. It takes into account properties due to some motion, okay, and will allow us to give a full equations, the full Maxwell equations that tell you exactly how an electric field, whether it's moving or static, will apply to a test charge. We'll meet some conservation laws, the continuity equation and Poynting's theorem. We'll think about the work done by a magnetic field, and we'll meet electromagnetic waves briefly and potentials. Then we'll end the course by thinking about some of the most magnificent ideas in theoretical physics, those of special relativity. So we'll look at Einstein's postulates, we'll look at time dilation, length contraction, the Lorentz transformations, proper time, proper velocity, relativistic energy and momentum, the Lorentz tensters, and finally we'll turn back and look at electrodynamics and see how we can write Maxwell's equations in arguably a much simpler and nicer form using relativistic notation. So that's the detailed overview of the course. I want to talk a bit about how the course will be delivered. So this year is unusual. The delivery will be by lectures, by video, and I will try and make the lectures as far as I can short and to the point of the topic we're discussing. Occasionally I think it will be sensible to go on a bit longer. So, and the videos will appear week by week. The lecture notes, I've taken over the course for the first time just a month ago, and the lecture notes are currently being rewritten. There are topics I wanted to do in different order, there's certain conventions I wanted to use in a slightly different way, and as you'll find for electromagnetism, almost everybody who does it uses their own special notation. In that sense, the course is tricky, because you learn it one way and then you have to adjust the notation to read it another way. The lecture notes from last year are all available online and are on the KEATS webpage, so if you want to read ahead, they are perfect for you. You will still have to be aware that maybe different conventions will be used, so just notation and just a convention or two here and there. Otherwise, everything that's covered in those notes will be exactly what we cover in the course here. I'm rewriting everything because I want the conventions and notation to be the same way. And my notes for each week's video lectures will have to appear, because they're being written as the videos are being recorded, week by week with the lecture notes. So I offer you an apology for this, but I thought actually rewriting the lecture notes would be bringing a big improvement. We'll have to see. The old lecture notes, though, are all available. There will, of course, be weekly problem sets and tutorials, and you will submit your problems to tutorial classes as usual. And we'll also have a weekly live session where we'll all meet up and discuss, and I will try my best to decode any of the confusions I've wrought or sowed in the lectures. Okay, that's the aim. Okay. There are lots of books, and I'm particularly conscious to say this to you at the beginning. No extra reading beyond the lecture notes will be necessary, but because of the situation that I'm writing the lecture notes in advance of your lectures, and you won't have them until the week before or the week of your lectures as we go on, if you want to read ahead, I'm going to recommend to you several of these many very good books. So I've got a list of them here. I also happen to have almost all of them with me, so I'm going to talk you through them too. You can find them again on the reading list on the course webpage. So let's have a little look at the books I like. So this is the book that I'm going to follow very, very closely in writing my lecture notes. All the good ideas from my lecture notes almost certainly will be due to Griffiths. Whenever Griffiths writes a textbook in mathematical physics, it's normally unbeatable. And if I can do better in any idea, I'll try my best, but I doubt it. So I will expect most of the notes will follow closely Griffiths' notes. It's a nice book, it's readable. It's the kind of text that, and you'll see he does exactly what we're going to do, reviews vector calculus at the beginning, and so on. It's the kind of text that every time you have a question, you see something written down and you think, oh, I get most of that calculation apart from that bit. In the next paragraph, he explained that bit. So it's just perfect, I think. It's really, really well done. This is a beautiful subject. There are lots of amazing, perfect takes on this course. Let me give you another one. So this is the Feynman Lectures on Physics, Volume 2. Okay. Now, this is where I read the quote from at the beginning of the course. Now, almost all of Volume 2, much of Volume 2 is on electromagnetism. And it's on lots of topics and practical things and very physical ideas as well as theoretical ideas that perhaps we won't be necessary for our course, but it's beautifully written. Let me give you a brief idea. But before I do that, let me say another thing. I'm recommending these texts. We're living in a time where it's going to be hard to get to the library. This text, however, is freely available online. Okay, so this will be the ideal, in my opinion, complement to what we're learning. It's the kind of text you could read after you've struggled through a week's lectures, and you can enjoy the subject when you read this. Okay, that's my feeling anyway. Let me just take you over to the web for a moment. So here we are on our KEATS course page for the course. Okay. Now, I'm just going to type into the search bar something very simple. I'm going to go Feynman Lectures Volume 2. In fact, Feynman Lectures will be enough. Let's just search Feynman Lectures. I'm searching with Google. The first entry that comes up is the Feynman Lectures hosted at Caltech. Okay, so thank you, Caltech. This is where Richard Feynman worked. They've put all the lectures online. Now, these are beautiful. They're not, I don't think, always the best source to learn something the first time from, but they are arguably the best source for relearning a subject or having learned a subject a little bit, going and getting that second deeper view. Okay, there are throwaway comments here that will leave you wondering if you just use this as your first source. The lectures on electromagnetism are particularly good, so that's volume 2. And if we go to electromagnetism over here, okay, we can see exactly the lectures I was discussing, okay, and he follows a similar path. Here you see the Lorentz force law, okay. So, just to give you an idea of why I think these are quite exciting texts, just read this first paragraph with me here. Consider a force like gravitation, which varies predominantly inversely as the square of the distance, but which is about a billion, 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 billion times stronger. And with another difference, there are two kinds of matter. Some which we can call positive and some which we call negative. Like kinds repel and unlike kinds attract. Unlike gravity, there is only attraction. What would happen? This is the essence of theoretical physics, by the way. Just saying a lot of mathematical things and then saying, now what happens? What does that lead to? And being happily rewarded when it has some bearing on reality. Let me go on though. He says a bunch of positives would repel with enormous force and spread out in all directions. A bunch of negatives would do the same. But an evenly mixed bunch of positives and negatives would do something completely different. The opposite pieces would be pulled together by the enormous attractions. The net result would be that the terrific forces would balance themselves out almost perfectly by forming tight, fine mixtures of the positive and the negative. And between two separate bunches of such mixtures, there would be practically no attraction or repulsion at all. He's, of course, just saying if you have a very strong force with positives and negatives, you'll get clumps of things which are neutral. And those are the building blocks of the universe. He goes on to talk about how strong the force is. This is stuff that leaves your mind, with space to enjoy the ideas. So after your lectures, consider dipping into the Feynman lectures. So they're on the reading list. Okay, they'll sometimes be off topic, sometimes be on topic, but they're beautiful and I think they're good fun and hopefully very rewarding. Okay. Again, just to say, you do not need to use any books at all because everything will be covered that you need in the lecture notes. I have a third book I really like. Okay, I guess you can tell I like the books because I've bought them all. So this is by Ashok Das. Now he's a bit like David Griffiths, in my opinion. Everything Ashok Das writes is just perfect. And it has that same feature. There's always, just after the questioning moment when you're reading something, Ashok Das then explains it to you. He seems to know what's going to be mystifying. So these are beautiful books. Okay, I recommend this again. I'm recommending so many books because, well, they're really good books. Okay, but on top of that, it's really a great idea to have different points of view and different languages to explain ideas to you. I'm going to explain it to you, the subject, the way I think is clearest, the way I think is most sensible. But different voices will have different views and will explain different ideas in better ways than me for you. Okay, so do explore the literature and have a look. Now, I've got a few books also on special relativity, which I'm also going to mention. The first one is kind of different. So this is in the series of books by Leonard Susskind called The Theoretical Minimum. Okay, so I think if you're thinking about theoretical physics and speciality, this might appeal to you. It's exactly on our topic. It's very, very readable, and it's quite, a fun read. But Okay, I mean, just have a quick look at the contents to see that it's a serious book. We've got Maxwell's equations here at 269. Let's just have a little look. 269. How does it look? Well, here we go, Maxwell's equations. Okay, now things are explained simply, but they are done mathematically. So, you know, it's a chatty book with everything done properly in it. And again, it's another good companion. So, you know, compare this with, say, the Feynman lectures. Also very talkative and interesting, and a companion to learning. For more mathematical texts for learning, well, here's the book I learnt, and many, many generations of mathematical physicists learnt special relativity from. It's by A.P. French. It's a classic book. Every single paradox in the subject that you would like to think of could be found, at least the beginnings of the ideas in the settings here and how to approach them in this book. Okay. When I was a student, I found this book simultaneously fascinating and also infuriating. I'm not going to tell you it's the best book, and it's not like, I don't think it's like the books I mentioned earlier where they seem to answer all the puzzles that come to your head. This book, I think, left me with puzzles, but still, it's short, it's to the point, and it's a good book, so it's not too long. Okay, and we'll do everything you need and give you a full introduction. For a fuller test, we could try this one, Special Relativity for the Enthusiastic Beginner by David Morin. Okay, so this is a much larger book. Again, all the paradoxes and interesting ideas will be covered in here. Let me take a brief look here. So you can see it begins with Maxwell's equations. Okay, and then we have time dilation, length contraction. For sure, on your first viewing of these ideas, they'll be confusing, and you will want, I think, to look them up in different sources. So my third book is another special relativity book, Introduction to Special Relativity by James H. Smith, okay, which also comes highly recommended. Okay, so these are the texts I would recommend for you, the 3 special relativity texts for you to go to when something seems immediately puzzling when we're talking about special relativity. Okay, but be assured, everyone who's ever studied special relativity immediately found it puzzling too. Okay, if you find it puzzling, it probably means you're thinking about it in just the right deep enough way. Okay, well, that's everything I wanted to say to you for this quick overview. I'm looking forward to writing the lecture notes fully and discussing with you and having made all my video lectures for you. I think it's a beautiful subject. I hope you'll enjoy it as much as I expect to. Okay, and I look forward to discussing with you by email and in the live sessions each week. All right, have fun.